had the chance to meet great people, and hopefully this is another opportunity for us to establish long time connections. Let me introduce the first speaker. It's Roby from Ross Math program and the Promise. He has been associated with these two programs for a long time, and he's an associate professor now at Cal State Hayward University. Tom?
Thank you very much, T2. So I have a couple of handouts going around, and maybe if you could do the honors, I'd really appreciate it. One of them is problem sets, 2 problem sets from the Ross program, vintage from 1983. So if you get bored anytime during this session, you've got something to look at. And the other is just a copy of the PowerPoint slides. I always hesitate to use PowerPoint, especially after Tufte's been going around telling everybody it makes us stupid. And he has good reasons for this, for sure, but at the same time, when you're giving a talk that's going to be on the web and is a reminder of the kinds of things I'm hoping to say. Oh yes, it might contain Far East text and formats, but fortunately it's not critical that you know how to write my name in kanji. So that's what these 5 squares are, even though it's only 4 characters. I don't know why it turns into 5 squares. That's another conundrum for the computer scientists among you. I think the first thing I'd like to do, though, is really thank everybody who's here and say how much I appreciate all the efforts of this vast community that's far wider than I think I originally realized. It's, as it's been made clear in several talks, this is a labor of love. This is not something people do because they're going to make quick money. In fact, a lot of people have been volunteering their time for decades with, and putting their own money into projects that they firmly believe in. So it's a much more evangelical kind of thing. And it's wonderful to have this support network because a lot of us have worked in, relative isolation from other people, and I hope we'll really keep that going afterwards. In my talk, I'll be talking about the Ross and Promise programs, and also some about Hampshire College Summer Studies in Mathematics, which I'm also associated with. And I guess I'd like to make clear that when I try to distinguish what are some of the key features of math programs that set them apart from competitions or circles, I'm not trying to at all to denigrate the work that goes out there. I think it's just a different kind of beast, and what's really important is that we understand what are the things that work better for different kinds of students, and that we direct appropriate students to places where their talents, where they'll have the most fun, where their talents will be the most useful. And let's see, there's some way to make this full size, right? F5 or something? Okay, great, thank you. So anyway, in case you don't know where Hayward is, that's one of the frequently asked questions. I should really put it on my website. But this is the San Francisco Bay Area, and we're in, San Francisco's here, Berkeley's across the bridge. And if you go down to this bridge that spans the middle of the bay, Hayward's on the opposite shore. So north of Palo Alto, which is down here, northeast of Palo Alto. It might change its name soon so that you'll have a much harder time figuring it out. They're going to be called Cal State East Bay if the Board of Trustees approves it. And that's a bone of contention on our campus. I've been arguing for Cal State Harvard if we really wanted to improve the prestige of the university, because it would be a minimal change. And the newspaper is arguing for Cal State eBay because the idea is that we're going to sell the name to the highest bidder. Oh yeah, and maybe it would improve the endowment. So here's the outline of my talk. I'll talk a bit about my background because I think it's relevant to this talk. Then I'll talk about the Arnold Ross program, about the Promise program at Boston University, the Hampshire College Summer Studies in Mathematics, and then a little bit of comparing and contrasting. And at the last minute I squeezed the references off the sheet I handed out to you and gave a perennial issues thing that I hope will lead to further discussion. So I started in the Ross program in 1979. I was a participant in 79 and 80, and I guess a junior counselor unofficially in 1980. And in 1981, there was sort of a dearth of senior counselors. I became the head counselor in 1981, sharing it with somebody, and then by myself in 82 and 83. These were rebuilding years in the Ross program, so I really got to see some of the trials and tribulations of transplanting something from one place to another. It had been in Chicago through 1978 for 4 years. Then when I was a graduate student, I got invited by Kelly to be senior staff at the Hampshire College Summer Studies in Mathematics, which was a great honor, and I tremendously enjoyed that. And it was especially revealing for me to see the contrast with the Ross program, because there's always been some kind of a friendly rivalry between the two programs. Sometimes not even totally friendly. I mean, you know, these rumors go around about what things are like of the other programs that aren't always completely flattering. So it was great to have the straight dope and to be able to, I mean, it's amazing that, you know, we have stereotypes about us as a community, but even within our community, we sometimes have these, you know, these ridiculous stereotypings of other programs and other kinds of things. So then the Promise program started in 1989, and I was the founding head counselor working with a team of counselors who were great, but who had not been through the program itself. So there was a lot of on-the-ground training to make that work. And I stayed with Promise through 1991 when I went to Japan, and it was harder to get back from the summer. And then I returned to Promise in 2000 to work with the high school students and the in-service teachers. So Promise added a teacher component, and other people have spoken to the value of that. In the last 4 years, I haven't done anything with talented high school students because I've been completely embroiled in trying to do K-12 outreach, because there was a limited window of big bucks to do that in California. And so I decided to do what I could in that arena while there was actually funding for it. So anybody else who's interested in those issues, particularly issues of, you know, training teachers and how that ties in with students and all that, I'd be very interested to talk to you later today or any time. So I grabbed this picture off the web of Arnold Ross, you know, wearing his bolo tie and looking approximately as he did in 1979 when I first met him, although I'm sure the picture's 20 years later. He just didn't seem to age. He looked the same for 40 years. He started the program when he was 50 years old and kept teaching in it for over 40 years. He was a totally remarkable man, and one of the few people that I sort of look up to. I mean, I think about people who had a profound influence on my life. Certainly Arnold Ross and the program, and, you know, everything I do, including my work with teachers, has been completely shaped by the things that I learned in the Ross program. So I'm dedicating this talk to him. So the Ross program actually started in Notre Dame in 1957, and so here I really need to thank there's a large Eastern European, but particularly Russian tradition represented in this room in terms of math circles, and Arnold Ross was actually another person who came from that Russian tradition. Some of his influences were Shutanovsky. He was born in Chicago, but then ended up going back to Russia, and it became the Soviet Union, and he was stuck there for a long time, and then only came back to Chicago when he was in his late teens, where he entered the University of Chicago. So it's an interesting story, which you should read in the AMS articles by Alan Jackson that are wonderful, that tell some of the stories about him. But so there's that tradition that heavily influenced it. And then also 1957 is, of course, Sputnik. So that's the other reason we have to thank the strong Russian tradition in science and mathematics, because it's what really got a large stream woke up the government, and there was large funding from NSF for these kinds of summer science training programs for a long time afterwards. So he was the chair at Notre Dame. He started it there. He moved to become the chair at Ohio State, ran it there for 11 years. He moved to Chicago for 4 years for various reasons that aren't worth going into here. Paul Sally and other people were involved in that. And a program continued in Chicago on and off, maybe even to this day, but certainly there was one in 1980 when there was still NSF money around to fund these things. I think that was about the last year for a while, and then Young Scholars kicked in. The Ross program is an 8-week residential summer program. It's multi-level, which is rare. NSF has not liked to fund multi-level programs. They like to get more people going through things, and so you go through your program and then you're done. You know, same thing with teacher training. You go to a 2-week institute and then you're trained. You've learned all you need to know about mathematics, and that's it. So you go back as a brilliant teacher. So the multi-level of it is really crucial because it becomes a kind of peer mentoring thing. I mean, people have talked about the importance of peers in all of this, and that's clearly a critical thing. But there's also, you know, it's not just a question of peers of equals. It's also the peer mentoring that goes on, where the counselors are the people who are really bringing along the younger generation. And Ross's point of view was much more hands-off. David Kelly may tell you more about that later. I mean, he would invite the students over to his house once during the program or something and almost never appeared in the dormitory. He sort of left, he trusted the counselors to do that kind of guidance and act as in loco parentis, or maybe just loco parentis. The basis of the first-year program are a brilliant collection of exploratory problem sets which were created and refined by Ross over the decades. And most of you, I hope I made enough handouts. I only made 50 copies, but I can make more if we need them. You'll have a sample of the problem set 0 with his famous aphorism, think deeply of simple things. And then on the back there's problem set 13, which sort of puts you in the thick of it, where you can, I mean, if you really understand number theory, you can probably see what numerical problems came before that led to the prove or disprove and salvage if possible problems that are there, and which proven, and so students hopefully have already conjectured something around the prove or disprove and salvage if possibles. Ross's lecturing style isn't what we think of as traditional lectures at all. His first job was to get 3 days behind. And then after that, he would try to stay 3 days behind and only talk in ways where he would be tying together ideas that students had already been struggling with in some ways. And I think Glenn Stevens and Dan continue that tradition. So if you just came into one lecture, I mean, if you were an NSF grants officer and you showed up at one of Ross's lectures, you would probably think that this guy was, had gone senile or something already and had no idea how to teach anything, because he wasn't teaching anything to you. He was doing something that was very integral to a problem that was focused around these problem sets. They've never been published, and I don't know if they could be really, but they're astonishing. Oh, here we go. So in the Ross program, students are encouraged to work together. I think actually I'm wrong. It's not a midterm and a final. That's promised. There's actually 2 exams and a final exam. But those are the only testing components, and the scores are private. These aren't, competition kinds of situation. The counselors really play a key role in marking the problem sense, giving hints, encouraging students, trying to get them back to work, serving as role models, because they're not just there to teach mathematics, they're also there to learn it. I guess I should talk more about that. So Ross had a wider range of unusual courses. My second year in the program, I remember, he decided, well, I'll invite Kurt Mahler from Canberra to come and teach p-adic analysis. So the world's greatest expert on p-adic analysis, a Fields Prize winner, is coming and teaching p-adic analysis to high school students in this program and college students, and there were some graduate students from Ohio State there as well. And then he said, okay, well, let's run a parallel track in real analysis that Bogdan-Baishansky did, so you can see, all right, this is how p-adic analysis works, this is how real analysis works, and you really got all these differences and, wonderful things like a series converges if and only if the nth term goes to 0, and all these things were brought out in it. It was very special, and he was always doing things like that, bringing experts in to talk about things that you wouldn't find ordinarily in the regular graduate school curriculum. So very much everything he did was meant to be enrichment, but if you got through all these things, you would be learning the skills that would make almost all your other coursework seem easy. Nobody should have abstract algebra before they've had a course in number theory, in my opinion. Everybody should see mods, and right? It's just, I think you said that earlier too, right? It's just, it's dead obvious, but anyway. Right. So yeah, here's the Russian influence. He was heavily influenced by Essos, Shatunovsky, and Odessa, and E.H. Moore in Chicago. So he used to joke. He'd say he'd call what he did Moore method, and then he'd say, "Oh, not R.L. Moore, E.H. Moore, the real Moore," right? Because R.L. Moore was actually a student of E.H. Moore, and though Ross was a student of L.E. Dixon, he was very heavily influenced by Moore's approach, which was again a kind of a Moore method, students trying to solve the problems presented by the instructor approach to doing mathematics. So there was large amounts of funding from NSF, and a lot of people know details of that more than I do. I wasn't directly involved in the funding when I was involved at the counseling level. It seems to be much harder nowadays to get funding all around, and the sources that I've heard about recent years that have sprung up that are really nice are the AMS Epsilon Fund and the Clay Foundation, which have been very helpful. The Promise program at Boston University was founded by two alumni of the Ross program, working with other alumni of the Ross program, Glenn Stevens and David Freed, who are both former counselors at Ross. And I think Glenn is pretty much taking over as the director of it, but Glenn and David and Margie Baruch, Steve Rosenberg, Ira Gessel, all these people basically teaching it every year. I think Ira's on an every other year program. It's modeled very closely on the Ross program, except it's only 6 weeks long. The problem sets are essentially 6 weeks worth of Ross problem sets. Ross changed the problem sets over time. In particular, when he started working with younger students in 1979, he had to do things that didn't assume quite as much background in algebra. But I remember talking to Glenn early on. You know, Glenn thought, well, you know, I'm a number theorist. I should be able to make changes to these. You know, and I can add things in and take things out. And so, you know, he started to tinker with them, and he kept finding that he would tinker with something on problem set 2, and then in problem set 24, it would come back to haunt him, because this crucial, you know, lemma for quadratic reciprocity or whatever, this crucial exploration that would help students get somewhere, had been missed out, and he hadn't realized that connection at the time. So if you ever get a chance to visit these programs and look closely over the problem sets, or better yet, experience it as a student or a counselor, it's just, it's really incredible. The difficulties of getting started, I think, are pretty clear when you start a program from scratch. A lot of you have this experience, but in this particular situation, you need counselors. They're really key to it. And so how do you find the counselors? Well, typically they're the people who came through your program, but you have a chicken and egg problem if you're starting a program. So in 1989, I and maybe only one other counselor had actually been through the Ross program before, and we were kept quite busy trying to help everybody out, figure out how to work with students working with these problems, how to give appropriate hints. And sometimes, you know, if you haven't worked through them yet, you don't know what's coming in problem set 13 and why this problem is so important for them to do. So I'll talk briefly about HCSS little IM. That's the correct acronym, not a typo. It's been founded and run by Kelly, and that's usually how everybody's called him in my presence, except for people who've known him for a long time. It's structured, it's more time structured. The Ross program isn't so much time structured as structured around problems, and except for an hour of lecture a day and maybe 3 hours of problem session a week that people don't really have to go to, the students are left free to work whenever they want. They can come to lecture and go home and take a nap and stay up till 3 in the morning, and a lot of them do, and that's fine. So the only thing that really keeps them working is the demand that they keep producing answers to these problems, and then their counselors will frequently say, this proof wasn't rigorous enough, can you rewrite this? And that kind of back and forth, the writing and rewriting process is the key thing that goes on. The Hampshire program, by contrast, will have 4-hour morning classes. A 4-hour morning class is, again, not a lecture. It's a much more interactive kind of thing. And then 3-hour problem sessions in the evening. The afternoons are blowing off steam and doing things more unstructured. There are also things like math films and people coming in to give talks. I think that happens in all the programs. It's more structured at Hampshire. So there's no exams or grades, which is just like Hampshire College itself, but students write self-evaluations, and then faculty write evaluations after looking at the students' self-evaluations. The atmosphere is trying to reduce the level of competitiveness as far as possible as you can in these kinds of situations, I think. So I've heard from people, I mean, the Ross program, I think, is less competitive than a math Olympiad competition for sure, but there still is a fairly strong competitive streak that tends to run through it. I mean, it's somehow natural and maybe also nurtured in people this age who've come from the contest solving scene. But it's not, Kelly is really trying to make sure that mathematics is inclusive, fun, relaxed, and so it certainly works better for a certain kind of student than some of the other atmospheres would. And Kelly can tell you a lot more about that since he's here. Comparisons with contests. So I've got compare and contrast here. I think that all these things provide much needed peer group support. If you're the only student who's interested in mathematics at your school, then you just feel isolated and you'd be tempted not to keep going with it. If you meet this peer group of people, either through contests or through a summer program or whatever, then you're very likely to think, oh, wow, this is fun. I like these people. Some people have mentioned how most of their friends are the people they met at MOP, not the people they met in their high school. It provides a much needed challenge for people that are bored with the standard curriculum, which is fairly common. It brings students into mathematics. It helps students with problem solving. So I think that these are things that pretty much describe everything that people do here. And so now somebody will contradict me later on, which is great. But I can't think of a counterexample right now. In contrast, I think that the competitive aspect of the summer program tends to be de-emphasized. People tend to go deeper into specific mathematical topics. I mean, certainly a program where by the 5th week students are proving the law of quadratic reciprocity on their own. I mean, on their own, but with help from counselors and lectures that are way behind where they are, is a pretty astonishing thing. And I mean, actually knowing the whole structure of how the proof builds from the axioms of arithmetic, right? Not just knowing the statement of the theorem and maybe how to apply it in numerical examples, which is sort of the best I'm afraid the best I can do with some of my students at an ordinary university. And there's a much more time for exploration. You have this thing where math content can really build because you're working with the students for day after day for a long period of time. It's a problem that we have in teacher professional development, where a lot of teacher training is one-shot deals, you know. Oh, we're going to do professional development on math this Saturday. And so you're never able to really work on the building of content knowledge that a lot of teachers haven't gotten for various reasons that I'm certainly not blaming them for. It helps bridge the gap from solving 5-second, 5-minute, or 5-hour problems to doing research. So, and here I'm echoing Joe Gallion. And I'd like to echo Joe Gallion again about, I once saw him give a talk where he said, suppose you write a paper that's co-authored with 2 other people and 2 more papers that are co-authored with 1 person. How many papers have you written? How many? 3 papers, right? That's 3 papers on your CV. Nobody says, oh, this is half a paper and this is a third of a paper. We're not adding fractions here. Nobody wants to do that. So, I mean, there's, you know, one of the stereotypes, well, nobody wants to add fractions. So one of the stereotypes that I think we all contend with is this idea that mathematics is done by 7 years of isolated struggle in your attic while your wife brings up your kids or something. So these stereotypes need to, I mean, especially the one about, you know, competition versus collaboration. I think it needs to be very clear to the outside world that collaboration is extremely important to mathematics nowadays. And I think you can get statistics in the AMS about the number of jointly co-authored papers 50 years ago and now, and there's been this dramatic upsurge, but I don't have those at the tip of my tongue. I'd like to really encourage everybody in this audience to send students to all these programs that are going to be discussed in this session and any other programs you know about. But I think what would be really helpful is if you can explain to them how it will be different from what they've already done. Because if they don't know what it is, if they come in expecting it to be a kind of, you know, Olympiad training or contest problem training, and if all their experience up to this point has been with solving contest problems, then a lot of this happens regularly in all the programs. Dan Shapiro emailed me about it when I asked him what he wanted me to talk about here, and he said in particular, and Kelly mentioned to me last night, that a lot of students come and say, oh, that's not what I wanted. I want to work on getting faster at solving problems. And that's fine. I mean, so those students need a different kind of program than the kinds of than Ross Hampshire or Promise. And so if you can sort of give students a sense for what these different programs are like, and especially if you can come visit them, these programs all welcome visitors, and have some sense yourself for what they're like, or send them to somebody who can tell them what they're like, that's a huge win over just saying, oh yeah, this is supposed to be a good program. Why don't you go there? it's just the miscommunicated expectations that get us into trouble here. Here are some perennial issues that I threw together when I was thinking, oh, my talk isn't really complete on the drive here. So diversity is a perennial issue, and you know, Ross was on the front lines on trying to make sure that his program wasn't just serving wealthy kids whose parents were university professors and trying to get people in from all sectors of the community. A perennial issue I'd really like to and I think this is an issue we all face. Another thing that I don't think has come up explicitly in this conference and that I think we really need to talk about is how to handle charges of elitism. Because I don't think it's just the programs that get this. I'm pretty sure that math circles will get this kind of thing, math competitions get this kind of thing, and it's really important when you're applying for funding to deal with this. You know, you'll get 2 or 3 reviewers who will say, well, this is basically an elitist program. You know, it's much more important that we work with these other populations. So we have to have all kinds of arguments that are reasonable and that make our case as well as possible that this isn't an elitist thing. So I feel like all of us are kind of misunderstood. And all of these things tie up with funding and public relations. So how can we collaborate to have better public relations? Because it's not that we should all be competing for the same limited pool of funding from Clay and Epsilon Foundation. It's that we should be increasing the vast pool of funding available for these things by making it very clear to everybody in terms that they understand, by trying to meet them halfway and explain to them just how important these programs are for kids, for the nation, for not leaving a certain segment of children behind. I mean, whatever terms you need, we have to get better at doing that. And then references have gotten much easier in the age of Google. So the references are Google Arnold Ross, Google Promise, Google HCSSIM. Google is not case dependent, so you don't need to capitalize Promise appropriately. Google Tom Roby, the first 3 pages are almost all me. Maybe you'll get my dad's poetry if you're not careful. And then there's this nice link about AMS link that has a list of a bunch of math camps that includes, I think, most of the ones here. And that, you can find that easily on the AMS website. So I think that's pretty much all I wanted to say. Thanks very much for your attention. Thanks.
Are there questions?
I was wondering, in the Hampshire program, why did it start at 34 hours and 17 hours in the evening?
Well, Kelly would really be the right person to ask that question of, but 17 plays a prominent role in the Hampshire College program. And I think the mystery of that has not been unraveled by just anyone. Yeah. Other questions about any of these things, I'd be happy to. How do you answer the charges of elitism? Well, I just asked the question, so I don't think it's fair to ask me to answer it off the cuff. But it's first of all important that we make clear that we are trying to reach out, trying to find talent wherever it is, and that we aren't just limiting the pool of people who come to us, taking a convenience sample of the population of the U.S. And I think for that we really need to work a lot harder and all work together and deal with these publicity issues. Another issue is that, I mean, we do have a lot of special programs in place for people who are struggling with mathematics, people who are struggling with English. There's a huge push in the state of California to deal with the question of English language learners. So, but it seems important also to pay attention to groups that are struggling with school for other reasons, because they're bored, they're not being challenged. And the amount of money that goes into these kinds of programs is far less than, I mean, isn't going to be disproportional to the amount of money that goes into work with other underrepresented groups. Yeah, Dimitri. So Dimitri's bringing up the baseball analogy.
And oh, okay. And they say, oh, you run a baseball camp for kids from this place in this case, and then this inner city or whatever. Well, isn't that elitist? I mean, come on. Well, we all know that. Well, what they do aspire in the end is, there are like 500 people in the entire country, and they have salaries like in excess of 5, 10, 20 million dollars. That's a purely elitist camp. I mean, what all these kids want to be the next Mike Piazza or something like that. Oh, I mean, come on. Compared to thousands of mathematicians or people doing pure math in the country, that could be, And the answer, of course, is that it's 90% of those kids will not become professional baseball players. They'll just play sports. They'll use that as a social outlet, to spend summer in, good places, communicate with the other kids, doing what they love, etc., etc., etc. It's, you could say almost the same thing about mathematics, not to mention that knowing and learning mathematics is, as we all know, very good and beneficial for, anything concerning high school education, etc., etc. Whereas you cannot always make the same connection with baseball, I'm sure. Or maybe you can.
Thank you. I think Harvey had a question, right? No, okay. I guess the other thing that is interesting to me is that this analogy with sports is a useful one for sure. I was thinking it's not totally perfect in the sense that the kinds of competitions that people do as related to math research, which is the professional end of things. There's a difference in quality. I mean, kids who are playing baseball are playing the same sport that the people in the major leagues play. It's not a difference. Maybe you disagree with that. Yeah, but it seems to me that basically what you play, football, baseball, that those sports have the same rules and the same kinds of. I mean, you're trying to throw it faster, harder, whatever. I mean, maybe there are these small technical differences, but there's a real difference in quality as well as just a real difference in the character of what you're doing when you make the transition from doing competitions to doing research math. So that there's something else there. Yeah, so let's see.
I'm not sure I've ever tried to articulate this before, but who in the world would ever think that what we offer to middle school and elementary school students, if they were special ed students, would be adequate? So suppose they go through the standard curriculum and they're a real special ed student where they can't grasp those concepts. Who in the world would think that was okay? So when we have these children who are just way beyond the standard curriculum in terms of deep thinking, not necessarily in terms of the specific algorithmic content, who would think that what we offer in the regular schools would even begin to approach to meet their needs? So I think that's really the best piece, because we have a special population here, just as real as any other, handicapped children from other perspectives. So when we put them in a regular school setting and we think that's it, that is a dreadful piece.
Thanks for the comment.
I just had a comment on the baseball analogy. I'd say the biggest difference is that the baseball camps aren't asking for NSF funding. And we are asking for public funding. We're asking for state and federal funding to support these programs. And I think that's a significant, so the charge of elitism does have to be met.
Just adding to that, I think the way to answer a charge of elitism is to say, yes, it is elitism, and we're asking public funding for it, and here's why it's good, and here's how it can be done inclusively. There's nothing wrong with elitism. I mean, it's just the society can decide to allocate resources in lots of ways, and as Mary Faye said, this is just another special education use of public funding. After all, we put public funding into the University of California system, which is by definition elitist. I think the most important thing that all of these programs, every single one of them, yours, everything, these programs that are in some sense by nature elitist need to be very good and better than they have been at inclusively finding talent. I mean, the word talent cannot be separated from this discussion, even if you define it differently. But what with all of this, all of I think what we're doing is nurturing talent, and I think what we're bad at collectively is finding talent, and finding it in a broad segment of the population.
Thanks for the comment.
It's great to have a journalist on our side.
A couple of things. I wanted to follow up what Paul said. It's important to distinguish charges of elitism with charges of underrepresentation of certain groups. Those are two different issues, but they frequently become confused, and it's just, there are various ways to sort that out. The business about finding talent applies even more to the issue of underrepresentation. I think as a community, we haven't been very good at doing that, not just finding, but developing talent. I've done work in South Queens, which is a heterogeneous, non-white, working class, and even lower population. And the kids' eyes light up. You can see that. They don't get this in classes, and nobody comes to do it with them. And most of my colleagues, and even I, don't have that much chance to get to do with them. The money isn't there, and the need isn't recognized. The second thing about baseball, I would argue that it is the same thing we're doing with those kids. It's on a different level, but it's the same thing. We're still throwing them problems and having them catch them, having them do it in a different structure from the classroom structure. And the third comment is there's another charge of elitism, which I'm wondering if other people haven't seen, and that is that it's not good for the child somehow to be with other kids. It encourages if they were a nerd in the class, why should we reward them being a nerd? And the important thing to see there, and I think I speak from experience, and I think many of you would also, that when kids are there with their intellectual peers, when they have a chance to show what they can do, then they shuck the defense of nerdism. They come out of their shell. They become very social. And I've seen this happen very graphically, and so many others of you have. That's an important thing to tell people, because even in education, that message has not gotten out.
Of course, my analogy is not, 100%, and I wanted to comment a little on the what Paul said. The pitch about that, yes, we are elitist, and that's good, and that now I will tell you why, is good probably when you're talking to somebody who really understands you, somebody in charge, in educated people, university people, something. I was trying to go more like for something closer to the earth, something that you would probably say to a high school principal maybe, or to education administration people in your state or something. And yes, a lot of baseball camps, not all of them, do not ask for funding. Some of them do still, but I would say that mathematics camps, mathematics circles, they should, this is not the right, basically, it's more related to the education, I would say, than baseball is, right? It's closer to the things that the schools should do. And it's, that's why it should be funded, Well, sports is a business, at least, the upper half of it, or so. So it's only natural that they have money, they have funding, et cetera, sponsors and sport teams coming to those camps, scouting, et cetera, so they pay for that. In mathematics, it's education, and we all, the state is naturally funding it. So, right, okay, thanks.
Wait.
To borrow a phrase from Arnold Ross, there are some very talented students that are inexperienced in mathematics. And what many of these programs look to are the students who have been identified as having some mathematical ability because they've been in environments where they've been able to experience things that perhaps other students haven't. And that's great. And I'm very much with what Paul said. Elitism isn't a bad thing if it's a democratic elitism that is spread over everyone. But part of that means that you have to take talent where it is. And this is, you saw in Arnold Ross's program, he adapted it as he went to lower level students in terms of their experience. And we should be thinking in those terms. There's a second point, and it's a critical mass of students of a certain sort, whatever that might be, and economically disadvantaged is one of those things. When you go to the Arnold Ross program, you are among students that are fairly well off. And the things that they eat in the dormitory are different than the things that you might eat and be comfortable with. And I was in a program at Case Western Reserve where for the first week of a 6 or 7 week residential, some of the students were sick for the first week because of the food, right? And, well, geez, we really don't want to deal with that kind of problem. Well, if you're going to dip into other talent bases, these are the kinds of things that you have to think about. But more than that, if the student is the only Hispanic student there, what sort of social pressure does that put on that student? And can you think in terms of, for these programs, some of which are large enough to even worry about it, having more than just, and I don't say it's token, I mean, you went out and you found this particular person and that's great, but you may need more than just one. And you may need a counselor that has sensitivity toward that sort of thing. Notice I didn't say a counselor like that. Mentoring goes across the board. People recognize mentors regardless of their race, gender, or sexual orientation. Thank you.
Yes?
Dmitry, I think I'm going to, in some sense, disagree with you. I think sports are as important as math. And I have seen this happening on the training of the Bulgarian team for the International Math Olympiad, where every weekend we were forced, quote unquote, to climb up one of the hills. They would just take us there and said, you have to do it. In the middle of the week, we had to go to swim, and so on. So as the Greeks, and those of us who were in Greece this summer, we have to be good in mind as well as in our body. So, and if you have gone to the training of the US math team, you would see that these kids actually play various sports. I think that, no, just saying that baseball is maybe not quite as close to education as sports is not, this is the part that I was just disagreeing with. So if we want to market these programs and get funds for them, it is quite okay to say that we are going to be including in our math, between our math activities, a lot of sports activities, and in fact, we will make sure that everyone participates in them. That's just a side remark.
I'd like to apologize for opening that can of worms too early in the session. Is there any chance we could?
I think we should move on to the next presenter. Then we'll have plenty of time at the end for discussions. The next speaker is Dave Kelly. He has been associated with the New Rochelle High School, the Princeton University, MIT, and Dartmouth. He has been the director of the Hampshire College Summer Studies in Mathematics since 1971. So please welcome him.
thank Tom for saying a lot about the summer studies already, so I can indulge myself and just tell some stories. He reminded me of the post-Sputnik era, which did lead to the initial funding of the summer studies, as well as many other programs. When I was in junior high school, there was the American Legion sponsored a Catch Up with the Russians essay contest. And this was the spirit of the thing. And my essay was that to catch up with the Russians, we should go on daylight savings time each year, but not go off. And this way we would gain a year, gain an hour each year. And I did some calculations, and it turned out that we would get to the year 2000 a full day and a half before the Russians. My junior high school English or social studies English teacher thought that was a great idea, and he submitted it to the county level. And we both got a reprimanding letter saying that it was flippancy like that that led to the Russians taking the lead in the first place. We should I have some other stories. As I approach senility, one of the things, and I think this is very significant in all of our lives, is the extent to which our job, both as teachers and as mathematicians, have been changed by computers. And when I was an undergraduate, I had to walk 2 miles to see a computer. And of course, that was in the snow with no shoes. And I find myself reminding my students every so often about how different learning mathematics, seeing things is and of course, you can carry big analogy, Newton never saw his basins of attraction. Julia never saw the beauty of the fractals. I'm reminded of one incident at the summer studies. Tom Banshaw, this was shortly after this was in the mid-70s, I guess. Tom Banshaw had just made the film on the hypercube, and he came up and showed the film to our students, and they were very impressed and enjoyed it. And then he had, as our speakers usually do, he stayed for lunch, and during the course of the luncheon conversation, he mentioned that he had unedited some rushes that he had made, some preliminary computer graphics for a film on the complex exponential function, and would we like to see it? And of course, everyone at the table said yes, and by the time we moved over to the East Lecture Hall to see the film, there was probably a crowd of 15 or 20 people there, most of the staff and a bunch of students. And he went to his car and pulled out a 16mm film, which is probably unfamiliar to many of you. And it was indeed unedited. It was a little spool of thread film. And he put it on. And I had, by that time in my career, already taught complex analysis. And everyone who has taught the complex analysis knows that the exponential function is the most important function in the world. And that it becomes even more important in complex land. And it's beautiful. It ties together the logarithmic and exponential function of real analysis with the circular functions. They're all there in this one function. But we didn't have four-dimensional graph paper at the time. And so to actually see a picture of it was quite, and the pictures weren't terribly well labeled. You sort of somehow had to sort of, what direction am I looking at the curve now? But you saw the exponential curve sort of weaving into the circular functions. And it ended very abruptly. And I was aware of the fact, as someone who was flicking on the lights behind me, I was aware of the fact that this was embarrassing. There were tears in my eyes. And the lights came on, and there were 4 other mathematicians in the room with tears in their eyes. This is the sort of thing that students don't appreciate now, just the power that has been brought to our mathematics. Later, when I began teaching, actually I was involved in summer programs for 10 years before coming to Hampshire. I was involved in, this was when time sharing was just coming in, and I was teaching at a program at St. Paul's School in Concord, New Hampshire, and instead of being, I told them that instead of having an assistant, what I wanted to do is arrange with Dartmouth to have a teletype connection to the computer up at Dartmouth. And this made, it made the rotogravure section and the Manchester Union Leader, high school students get to see a computer. And of course, we had one computer. All the students were working on this, and I gave them an exercise that essentially amounted to iteratively doubling the number of sides of a polygon inscribed in a circle, and used that to estimate pi. And the students, collaborated, worked the program, and came to me with this yellow printout, and they said, "This is very strange. The perimeters get closer and closer to pi, and then they exceed pi for a while, and then go back down." And it took me a few seconds to realize that what they were doing, of course, was multiplying by a very large number, a very, very tiny side, and a round-off error in that tiny side multiplied by a big number was actually causing this error. But instead of saying that, I said, "Aha, you've discovered the Gauss effect." Gauss was the first one to notice that these perimeters get bigger than the circle and then shrink back down. And a few students laughed, as you just did, and I didn't think much of it. Later on, we talked about it, round-off error and that sort of thing. I was giving a talk 3 or 4 years later to the NCTM, to a regional meeting of the NCTM, and after my talk, a teacher came up to me and said, "Are you the Professor Kelly who taught at St. Paul's School a number of years ago?" And I allowed as how I was. I shouldn't have. And she said, "Well, one of your students told me about the Gauss effect. And I have been searching the literature, and I can find no reference to the..." Be careful of what you say. Many of us remember, I'm on a roll now, you got to stop me at some point. The first scientific calculator that was readily available was, I don't know, TI-10 or something like that, and had a red liquid display. It was powered by a 9-volt battery, and the cases for 9-volt batteries, the lid always breaks off, and so there was this image of people sort of wandering around these calculators with these 2 thin wires and a 9-volt battery bouncing around on their side. Well, I found one of those, it still worked, at a tag sale, and I brought it into an evening problem session at the summer studies. This was maybe 10 years ago now, and the students sort of gathered around it, and they looked at this thing, and one student said, "Gee, I didn't know they could make calculators that big." Perhaps a more specific point on the computers to the program. In many years, not all years, we've talked about fractional linear transformations, a nice blend of geometry and algebra and complex numbers and such, and frequently talk about the invariance of the cross ratio there. And I sort of have 3 ways. I make sure that they all understand from a geometric point of view what that invariance is telling them about the cross ratios. But then to prove that the cross ratio is invariant, there's sort of a mechanical way, just write down the cross ratio, replace each z by az plus b over cz plus d, and do a lot of arithmetic, and by golly, it turns out to be the same cross ratio that you started with. And there's a much more elegant way of doing it, which is to recognize that every fractional linear transformation is the composition of a translation, a dilative rotation, and a reciprocation, and to show that each one of them preserves the cross ratio, and therefore the composition will also preserve the cross ratio. And then there's a really elegant way, which is just to recognize and use very subtly the fact that the map z into the cross ratio of z with 3 other complex numbers is itself a fractional linear transformation. And last summer, I was prepared to have students work on all these 3 things, and before I had stated the problem, a student had plugged it into Mathematica and had Mathematica simplify the expressions. I see it's the same thing. And this is sort of, I don't know. I don't know whether we've lost something there or not. In any event, I wanted to, again, thank the organizers for this conference and point out the obvious. Is there any way I can, these things are really crazy. There's no way of, we're all both trying to serve the next generation of mathematicians, but also speak a little bit more broadly and educate the broader community as to the power and beauty of mathematics. And there are various ways of doing this. And we've talked primarily about competition circles and camps. And since we're aiming for roughly the same goal and have different ways of getting there, that suggests the Bacchistochrome. And I wanted to organize some thoughts looking sort of a consumer's report type evaluation of competition circles and camps. And I would encourage you to, as some people already are, to be thinking of other models, preferably beginning with C. And rank these according to the criteria suggested, lovely mnemonic device by the word Bacchistochrome. And the first of these, the B is Broma. And this stands for broad range of mathematical activities. I would like to have it be full range of mathematical activities, but who's ever heard of a Framixtochrome? There's problem solving, to be sure, but there's also problem creating, there's also theory building, there's making conjectures, looking at data, looking for patterns, testing your conjectures, formulating your conjectures precisely, making definitions, searching for proofs of theorems, writing, a tremendously important part, board work, communicating mathematical ideas, generalizing. All of these things are important parts of being a mathematician. We try to include all of them in the Hampshire College Summer Studies, along with reading recent papers. This is always a feature. We pick up a few papers and students get together and collaboratively plow through reading a mathematical paper. Talking to visitors. We have a wide range of mathematicians coming through, and we make a point of having students interview visiting mathematicians and writing up the interview for the program journal, which is another good writing activity. It includes class summaries, good problems and such. The students put together a weekly program journal, which lets students from one class know what's going on in the other class, and so on. And so, for the broad range of mathematical activities, camps gets a red circle. I guess red is bad for consumers' reports, but it's good here. It means real good, as a matter of fact, red for real good. Another aspect of the camps, for the most part, that we're talking about is the residential nature. I think this is a tremendously important opportunity. The Hampshire program is a bit more residential than is sane in that the entire faculty live in the dorm with students. And in addition to having 8 hours of classes a day, a primetime theorem, weekend activities on Sundays, we have classes on Saturday, weekend activities on Sundays, the faculty live in the dorm with the students, eat meals, recreate with the students. This, I think, gives students a much better sense of what it is to be a mathematician. They see that mathematicians aren't just people who stand up in front of a lecture and then disappear for the rest of the day. There are ways in which this is, I think it's important. It's hard with the schedule such as the summer studies to get a family to participate. Usually it's a question of a spouse surrendering his or her spouse to the summer studies for 6 weeks. But occasionally we're able to bring a family on board for the summer. And this has sometimes led to very touching things. I remember one of our alums and staff members, Benji Fisher, also an Olympian. Benji Fisher was on campus with his 4 or 5-year-old daughter Alice one summer, and he and Alice were up ahead of us on the way to lunch, and I was talking with somebody else, but able to hear conversation between two students directly in front of me. And one student said, "Gee, I don't think my father ever talked to me the way Benji talks to his daughter." This is, I mean, it's a sad thing to hear, but I think it's important that they realize it's another sort of familial thing, the mathematical genealogy. We have frequently brought to campus, sometimes as a team, sometimes you just happen to be there, the thesis advisor of a current graduate student. And our students learn a lot by watching the interaction, watching a mentor and a student at a slightly higher level. So we scored very well on the residential aspect of the program. Assets. Incidentally, I'm not going to fill in the blanks for these other things. I'll let you. I'll let you do those rankings. Assets. The big asset of these programs, indeed most programs, are the alums. These are the people who, first of all, give you tremendous gratification in terms of, have I done anything good? Tied to assets loosely is when the National Science Foundation most recently pulled out of funding, this pushed me into a sort of a late career change of having to be a fundraiser. And this is something that I find generally uncomfortable, and I don't recommend it if you can avoid doing it. I feel very good that I still don't own a coat and tie, and that to be a fundraiser without a coat and tie is somewhat unusual. But this forced me to write to the alums of some 25 years of summer programs. And while gratifyingly we got a lot of money and have kept the program running largely with that and Epsilon support and odds and ends from other places, but the thing that was tremendously valuable and exciting and gratifying was to get comments from people who had been in the program 25 years ago who I haven't heard from for 25 years, saying how this program had such a great effect on them. Every teacher, there ought to be this thing in teacherdom that after a certain age you are required to make contact with all of your former students. And by and large, the students who didn't like you aren't going to respond. That's not universally true, but by and large, you get some very rewarding, and you know, teaching is one of the things that tends to have sort of long-range rewards, you know, long delayed gratification, but it's something that's particularly useful and helpful. Community. We're all involved in building mathematical communities of various levels. At the most elementary, smallest level, we're dealing with collaboration, students working together or working with a mentor, and this sort of expands to the whole program. There are all sorts of mathematical communities going out there. There's the IMO, there are the Putnam, there are REUs, the Budapest semesters, Project Next, Fellows, Putnam. All of these are communities within the world of mathematics. Some of them are bigger communities, some of them are smaller communities. One of the things that I think people ought to be concerned about is trying to facilitate the maintenance of the community. One of the things that I would like to say that this was very carefully designed, but I have to confess it just sort of happened, but the yellow pig. This has become the emblem of the summer studies with no explanation when we accept a student to the summer studies. In the invitation packet is a little yellow pig. And we don't explain it, we don't say anything about it. Later on we tell them that if they had been carefully observing things, they would have noticed that we had, in several of our letters, the initial letters of the sentences spelled out yellow pig. You know, your application has been received, enclosed, please find, look forward to, blah, blah, blah. But don't tell any. Tell students to apply, but don't tell them to look for that. But then when it comes time to pick students up at the airport, the person doing the picking up carries a yellow pig. And this is sort of the last part of the interesting test that we use to select students. If they don't recognize who it is that's there to pick them up, they wind up going to another program. H is for hours. And this is a tremendously important. We have all this time. There's no rush. We can go down dead ends. I mean, what can be more valuable than going down a dead end and recognizing that it's a dead end after a while. Important also, I from time to time I was a reviewer for NSF proposals for summer programs, and I was amazed, and of course I had a bit of experience, but I was amazed at the number of people who write proposals for residential programs and don't mention anything about what happens outside of class. I mean, an awful lot of things happen outside of class. I think we've hit upon a good strategy of having problem sessions in the evening and having the free time being in the afternoons when they can play frisbee, swim, hike, bike, and so on. They're much less likely to get into trouble in the middle of the afternoon than they are if they're free and unguided at 11 o'clock or midnight. But the after hours, along these lines, contact hours. With our students, we have more contact hours, and this is in small groups. We have classes of about 15 students with 3 staff members, an old person like me and a graduate student or math major, 2 of them, a 1-to-5 ratio, faculty to students. And we have contact with them for 8 hours a day in classroom type settings, and another 16 hours sleeping, not together, but, eating together, recreating together. We have more contact with them. Just the straight academic is more in a week than a college course has in a semester. And so it's not surprising, especially when they're leading the way and they're bright, and, they're pulling you. You're not trying to drag them through material, but they're pushing the way, they're making the conjectures. We regularly cover more than 2 college courses. Impact. Here, the impact, of course, is greatest on the individual students, but it's surprising the amount of impact this has on their communities when they go back home. In its wisdom, I think that the National Science Foundation, when it was supporting these programs, made a number of, I think, fairly serious tactical mistakes. But one of the things that they had briefly, it was like clearly somebody's idea, and it got included in the guidelines for a while, and then after that it wasn't heard of later, but it was one thing that sort of lasted in our documentation at least. The National Science Foundation used to require students to agree to give a talk when they went back to their high schools. And it's a fairly simple thing, but it turns out that actually was very good. First of all, students think while they're in the program, what am I going to tell my students? But then they go back and they spread an enthusiasm. Frequently they teach their teacher something in a fairly non-competitive, non-aggressive, aggressive sort of way. We do have, and I recommend this for all of you who deal with talented students, we have toward the end of our program a debriefing period. We just have a primetime talk where we tell students some of the things to be worried about or to be concerned about when they get back to school. First of all, we try to give them lots of resources, other ways in which they can continue their mathematical lives. But after the second summer program, I got a letter from a high school teacher of one of our students, a sponsoring teacher, and she wrote that she would never again allow one of her students to come to my program because that student returned so full of arrogance, acted as if he knew everything. And reading between the lines, I saw that he may have let on that he knew something that she didn't know. But I tell students that one of the things you've learned here, certainly, is that you don't know everything. And if you get back to your school and a teacher or even another student comes out thinking inferior, thinking that they are somehow inferior to you in terms of their knowledge, in terms of their ability, then you have failed. It's not a question of the student, the teacher having failed, but you have failed. Spreading the word, I think, is an important thing. What happened to my red pen? Well, there, blue also means very good. Selecting students is I feel kind of guilty when I say spreading the word. I think one thing that has come up a couple of times at these meetings, and something that I think we always have to bear in mind, is that we are in a very enviable, I feel sometimes almost guilty situation in that we choose our students, we choose our faculty, we choose our curriculum. We're not pressured by grades. We're not pressured by a syllabus that we have to get through. And sometimes when I'm talking to a high school teacher about this opportunity, I somehow sort of feel guilty, oh my God, what they have to put up with. I think we make a mistake just by pouring money on problems. I think especially in the context of the various types of programs that we have, making one group of students feel inferior because they're not getting full freight paid for them, creating financial incentive, turning students into mercenaries too soon, I think is a serious problem. But I don't think we can spend too much money on the secondary community. And one of the things that we have to be aware of when we lament the fact that a student can go to her teacher and be told that there are no other things other than this one opportunity out there. There are no other better problems. We have to realize that a teacher who can do anything outside of the things that are demanded of him or her, anything at all, is to be commended. And we just can't expect the teachers to know all of the options out there. And this is one of the things that we have to do, somehow spread the word. And I think it's important also that we actually serve the people that we bring into the program. This appropriate role models. True, anyone can be a mentor, but I think it's important that a program that is 40% Asian American should see an Asian American faculty member, staff member from time to time, especially certainly this is true for women. This past summer we hit 30%, 33% women in the program, and that was a high for in recent times. And I think many of you know that's a very high for many other programs. And we've always had some very good women, but I think it's important to realize that they and other groups require special attention. One of the things that the Sommer Studies has an institutional membership in the Association for Women in Mathematics, and this allows us to give subscriptions to the journal to a handful of students each year. I think it's very important. One of the things that has been mentioned from time to time, but I think is critically important, and that is the role of the summer camps in teacher training. An awful lot of our junior staff members especially, these people sometimes in graduate school, sometimes still undergraduate math majors, have their first true and idealized type of situation, but their first teaching experiences. There are there are dozens of some of the best teachers in mathematics around now who say that they got their teaching experience. They got turned on to teaching. They realized how good it could be by participating in the summer studies. And there are teachers, they're teachers, you probably know of such teachers. A lot of our classrooms are sort of open. Sometimes we just do things in a lounge or a lobby around a clipboard. Some of the classrooms at Hampshire actually sort of don't have real doors. And I and many of my Hampshire colleagues, both in and out of math, have frequently been transfixed. They'll sort of stop and just watch a classroom. We saw some of it in the math circles. It's just powerful stuff to watch good teaching going on. And a lot of teaching training, teacher training, takes place in these programs. And I think that the place where these people get the idea of teaching in the program frequently is by having been students in the program. And I think that anything that prevents good teachers from getting involved in these potential good teachers getting involved in these programs is a loss to the whole mathematical community. Ownership. It's very important. That sort of happens inevitably in the type of programs that we're thinking of, less probably with the Olympiad, but students take ownership of an idea, of a problem. Most of you are familiar with naming a conjecture after the person who made it. And this can sometimes be embarrassing when a student later finds out that Lagrange's theorem isn't really Joe's theorem, it's Lagrange's theorem. Again, you're always learning from students. One student, in writing his final introspection, we have students write, one I think responsibility for having had the amount of contact hours that we have with students is at the end of the summer we write a very detailed evaluation of that student's work. This is frequently two single space size of paper, and people were talking about, what is the reward for students to participate in the program? Well, this is something that helps them get into college. It's certainly the most incisive, accurate, intensive evaluation that student is likely to get. He's never going to have that many faculty working that closely with him at any other point in his or her academic career. So writing the evaluations is important, but we also ask the students to write a self-evaluation, not an evaluation of the program, we ask for that too, but an evaluation of his or her own work at the midpoint of the program. And that's important because this gives us a chance to see what's going on if we haven't noticed it in the student's head. And also it allows for mid-course corrections, and we can say, well, no, wait a minute, why don't you think you're doing this? Can you think of any strategies for improving this? Making students feel a responsibility for their own education. We have a maxi mini catalog for the second half of the summer, and students choose their courses for the second half of the summer. Now, frequently we have to guide them and tell them that their preferences aren't right. We have to correct them from time to time. But it's a sense of empowerment that they own this. I started to say one student very proudly in his final introspection said, and the thing that I feel best about is that I had more wrong conjectures than anyone else in the class. Well, that's wonderful. That's what we're all about. Thank you. Change. I've mentioned some of the changes that have occurred during the program. Let me just. Black also means very good. And, my 2-minute warning came just in time because you own the rest of the crone. A minute and a half for questions that people want to ask, and then others will come after the general session, I assume. Paul.
Has the sort of non-competitive nature of the program changed coming from like the countercultural 70s to now? I would think that the kind of students and parents especially that you're getting have changed. I just wonder if you could just talk about that.
It's changed minimally. I think I was mentioning before the session began, 2 horrendous experiences that we had. Actually we had 3. One a long time ago, a sponsoring teacher had essentially done the interesting test for the student. And I found that professionally very unethical. It was certainly unfair to the student. And I felt sufficiently disturbed about it that I felt obligated to both talk to the student and his immediate supervisor. We have had 2 instances now of a father doing the interesting test. In one case, a very bizarre situation, the father acted surprised that he wasn't going to be allowed to come from Texas and stay with his student during the program. And at first I thought this was just really strange. And I kept saying, well, why do you want to do this? And he said things like, well, suppose X catches a cold. Well, he may catch a cold. It didn't seem to be a monumental problem. But it turned out that in the second day of the program, it was already apparent that not only hadn't the student done the interesting test, but hadn't even understood what he purportedly wrote on the interesting test. And that was a very painful situation. By and large, though, while we have students coming from different backgrounds, different levels of competitiveness, we do try to catch before the selection process is over, we try to catch students whose only interest in mathematics is to do well in contests and something. And occasionally we do have somebody who still gets through the program for whom it's not appropriate. More commonly, and this is especially true of the males, they come understandably knowing that they're the big mathematician in their school, and they're out to impress other people how much they know. We make a big point of saying that we don't care how much you know. What we're interested in is how much you grow. We tell students that they're not to blurt out answers if they've seen a problem. It does put a responsibility on us to pick problems where, or to phrase problems in such a way that it puts students on sort of a common ground. We don't as some other programs do. We don't partition students according to their backgrounds or according to their abilities, but we try to present topics that they're very unlikely to have seen. But still, especially in the evening problem sessions, there are times when we have to, when we, the staff, who sort of circulate amongst the problem groups, there are times when we have to correct their social attitudes and just sort of say, you know, my golly, you've been speaking 80% of the time. Don't you know how to listen? And sometimes, I discover sort of a sneaky joy in stepping on somebody who gets too aggressive. And they catch the message pretty quickly. But something that we do have to be aware of. One more.
I am glad that you addressed some issues, perhaps unintentionally, and answered the whole question about elitism or elitism, because you brought the issues of both social responsibility and human sensibility as part of an education. And I think that what I've perceived is that many people, when they think about a good mathematics education, I think they miss the point, because a good education is supposed to awaken our human sensibility. And if what it makes of us is a group of arrogant human beings that somehow treat other people with disdain, I think that we have failed as educators and we have failed as mathematicians. And to address again the issue of elitism, to me, elitism is when you foster a group that is arrogant in nature. And that is, I mean, a group that has certain qualities is one thing, and when you try to foster those qualities, nurture those qualities, and share them then with other human beings around you, I think that makes you a better human being. And I think you have made one of the most enlightening, given one of the most enlightening talks during these 3-day workshop, and I just wanted to thank you for that.
I didn't say when I talked about the sort of the full range of mathematical activities. I think a big distinction to be made there is that I think, and all of us are aware of this at various levels of explicitness, is that what we are teaching is mathematics as a collection of processes, as a way of thinking. It's not a collection of results. And quite frequently what people tend to get arrogant about is this big tool bag of facts that they know. And that, I think, is something that there's no particular reason why they or anyone else should be proud of that. While I'm all in favor of, as you may have guessed, in getting camps sort of up front, I mean, the title of this conference sort of, I mean, we're invited, and I'm delighted for the participation, but the title itself doesn't involve the word camps, and I think this is a significant omission. However, if you're running a program such as ours in Massachusetts, you cannot use the word camp. If the Commonwealth of Massachusetts classifies you as a camp, the amount of regulations that you're forced to do make teaching mathematics totally impossible. We would have to fill out a form literally in triplicate if we wanted to give an aspirin to a student who was complaining of a headache. Okay? So don't use the word camp if you're talking to anyone in the Commonwealth of Massachusetts.
Our next presenter is Rick Sommer. Rick is at Stanford University and serves as Deputy Director for the Education Program for Gifted Youth. He's also a Director of Stanford University Mathematics Camp. Rick?
Thank you very much. And first of all, I would like to thank the organizers. This has been a great experience for me, and I'm honored to be part of this community of people that are doing such substantial work to build the mathematics community. And also I'm honored to be a part of this session, and I think that David Kelly and Tom Roby have given excellent introductions to math camps in general and cover a lot of ground that I think is common to all of our programs. So that makes my job a little bit easier, because a lot of what if I was the only speaker, a lot of what I would be saying has already been said. I'm here to talk about the Stanford Math Camp, also known as SUMAC. This program was founded in 1995, or the first summer of activity in 1995. The funding was obtained in 1994. Professors Ralph Cohen and Rafe Matseo are the founders of the program, and I joined them very early on, and I've been teaching for SUMAC ever since it began, and I've been very much involved in organizing the program and developing it over the last, we're going on our 11th year. Rafe Matseo and I are the co-directors of the program. I'm going to say a little bit about the structure of the program just to give you some specifics that maybe distinguish our program from the others. Rafe Matseo also instructs in the program, and I'm going to say more about that later. Like the other camps that have been mentioned today, we're about, lots of different things. Part of it is mathematical enrichment for talented high school students. It's about intensive study in mathematics. I think a key component to all of these programs, of course, is the social environment of having students with similar interests and abilities in mathematics all together in the same place for an extended period, living together, eating together, playing together. These students, the typical student is coming from their experience at home is they're living in isolation as far as mathematics goes. And this is something that makes it much different than baseball camp, where everybody understands baseball. But the experience of the students that arrive at math camp is nobody at home understands them. Their parents don't understand them. Their teachers don't understand them. And suddenly they're in an environment where a bunch of other kids just like them as far as mathematics goes. A diverse group when you look at other qualities. And they're living with undergraduate math majors and math graduate students, and math faculty are around all the time, and everybody, there's this common ground in mathematics, and they can talk about math problems over a game of pool, or while they're playing basketball, or at dinner, any time of the day. They can bring up a math problem. It could be related to the material that's covered in the program, or it could be something completely different, and there's somebody there to talk about it. And I think that makes it a very special experience, as we all know. So regarding the specifics of SUMAC, one of the, I'll name a few features of it, just looking at the structure of a typical day. The students spend a couple of hours in class. There are two different courses. I teach one. Rafe Matseo has been teaching the other. About 2/3 of the students are in my course, and the other third are in his course. Similar to both courses is the students have a certain amount of class time. At the end of class, they get a problem set that fills up the morning, the classroom time does. They go to lunch, and then after lunch, they begin working on their problem sets. They spend a lot more time working on problems than they do in class, so it's very much about learning mathematics through doing it. And so their afternoons, they're in kind of a structured study hall period at the residence. We have this really beautiful residence that was a single-family mansion way back in the 20s and has been converted to a student residence. And it's a very special place. There are lots of nice common areas that the students can hang out in and work on their problem sets. Also in the afternoons, they meet in one-on-one sessions with their TAs. The TAs consist of the residential staff, so they're math graduate students and undergraduate math majors. We have additional graduate students coming in to serve in this role, and each TA has about 5 students that they're overseeing in their daily work. So the students will meet in one-on-one sessions with their TAs for roughly half an hour or so each day, sometimes longer. And there they get, kind of intensive one-on-one instruction. This allows for a very individualized experience, which I think is another component that makes it very a special program. So even though these are all hotshot math students, back home, there's a range of abilities and backgrounds and experience when they get there. And we individualize the instruction through these one-on-one sessions. So adjustments can be made so that every student is challenged and every student has a sense of accomplishment on a daily basis. So students who have maybe seen some material before might get some extra problems. Students who are struggling get whatever it takes to fill in the gaps in their background so they can understand what's going on. So that's a typical day, at least 4 days a week. 1 day a week they engage in a different component of the program, which is led by the TAs. We call it the research project. It's not original research in mathematics. It's more of the book report type research where you're looking at papers, chapters in textbooks, internet, or talking to faculty in the math department. And it's on subtopics of the main course. This leads up, so they have these kind of seminar style discussions with their TAs, working first as a group and then later on independently, culminating in a presentation at the end of the program where they present to their whole class. I wanted to also say a little bit about the topics. I'll speak mainly at the topics I cover in one of the two courses. For lack of a better name, we call them Program 1 and Program 2. So these are the so-called Program 1 topics. The core material is abstract algebra. So students get an introduction to group theory, a little bit about rings and fields as well. And the way that it's presented is I use some motivating problems or topic areas that are meant to draw from important historical results in mathematics, as well as recent research and applications in mathematics. So there are 5 topic areas, and these also, they serve both as motivational material for the course, as well as the subtopics for the research groups. So they're unconstructability, cryptography, coding theory, the mathematics of the Rubik's Cube, and classifying patterns in 2 dimensions. And so these are things that I can explain on the first day, and they can understand the nature of the question that's being asked. And then through the course, they're learning they're getting some core material that could be used to help understand and solve problems related to these topics. And then when they meet 1 day a week in their research groups, they can dig in deep into these topics and specialize and look at one particular aspect of it. And I think this works very well. Even though some of the students would come into a program like this and love the opportunity to just study pure mathematics, but others need a little bit more in order to engage them. And I think that this works for both groups. So anyway, that's the overview of the Program 1 material. Program 2, well, that has changed over the years, but for the last 3 or 4 years, it's been algebraic topology. The program is, the course is a similar style where the students will work in a research project, a subtopic of the main course. Okay. I also wanted to say a little bit about who attends our program. We've been maintaining a level of about 35 or 36 students for almost since the beginning. That's what our residence accommodates, and we like our residents a lot, so we're not going to change that. The gender split, we have about 45% female. Been maintaining that over the last several years. And we're able to do that mainly because the small size and the fact that we get many more applications than we're able to accommodate. And we're turning away lots and lots of good students, both male and female. But we do get probably 3 or 4 times as many male applicants as female applicants. As far as geographic distribution, every year we get about 5 or 6 international students. We get, students from across the U.S., more from California than any other state, but still at least a dozen states are represented each year. In addition to the international students, we get a lot of immigrants to the U.S., mainly from Eastern Europe or Asia. So there's very much an international feel during the program. I wanted to name some of the countries that we've had students come from. Azerbaijan, Belgium, Bulgaria, Canada, Germany, Italy, Jamaica, Korea, Latvia, Luxembourg, Republic of Moldova, Saudi Arabia, Serbia, Singapore, Spain, Sweden, Taiwan, Thailand, and Turkey. So you can see, well, some expected places, certainly a representation from Asia, for example, but then some unexpected places too. Republic of Moldova and Azerbaijan, for example. 2 years ago, I know that the students did a count of how many languages were spoken among the group, and it was over 20, and that surprised me. But so even though, so there's a diversity there in geographic distribution. We get diversity in terms of both students from urban settings and rural settings. We get a small amount of diversity as far as underrepresented minorities, not nearly as much as we'd like. We do have quite a bit of financial aid. We're funded by a grant from the Howard Hughes Foundation. So we are able to support disadvantaged kids, but the problem, of course, is recruiting them. And I think this is a problem that's faced in all of the different programs that are represented here. One of the things also that we attempt in our admissions is to seek out students who would not have opportunities like this otherwise. So it's easy to target specific groups. For example, if you use AMC results, it's a good way to get strong math students. But a lot of students might be overlooked. Students who have mathematical talent but are not in environments where they have other mathematical opportunities. For example, if they're at a high school that doesn't offer the AMC exams. In order to give those students an opportunity, we look at many other things and not just test scores, and we try to, in our recruitment, do what we can to target places that wouldn't otherwise provide opportunities. In our first couple of years, and it's unfortunate we can't afford to do this anymore, we sent letters to every single high school in California, and high schools in every corner of the state. And when we were able to do that, we'd draw students out of these rural communities, completely unexpected, and that kind of mailing did very little to get students from the urban communities, because I think the big urban school districts, they get mailings like this all the time. But these little schools in out of the way places, to get something inviting them to send students to Stanford University is a lot more rare. And so we're always looking for other ways to do that. I wanted to comment a little bit on the value of the program, well, to me, to the students, to Stanford. As far as to Stanford University, to the math department, this is very much a part of the math department. We involve undergraduates, graduate students, and faculty. It serves as a community building tool for all of those groups, especially the graduate students and undergraduates. It's a good way for them to spend some time during the summer, and it gets them some teaching experience. They enjoy it, I think, at least as much as the students that attend. It also serves somewhat as a recruitment tool. Roby Abigail yesterday said that it's going to be a long time before Stanford has a Putnam exam winner, but efforts are made to draw good students to the math department, and that was part of the original conception of the program. Not necessarily that it's all about Putnam exam, but it's about students who have an appreciation for mathematics, and not just students who are going to become math majors. I mean, we want students in all disciplines at Stanford who have an understanding and an appreciation of mathematics. And so certainly a good many of our students at SUMAC have their eyes on Stanford for undergraduate, and but not all of them want to be math majors, and that's fine. Let's see. Right, so as far as the value for the students, of course, knowing more math is part of it. The specific mathematical content, I think, is only a small part. Having an appreciation of mathematics, having an understanding of how mathematics works, knowing what it's like to be, having that introduction to undergraduate life and graduate student life and life as a research mathematician, like nowhere else. I didn't get those experiences until I was already in college, and it would have been great to have those exposure to that at an earlier age. They also develop lifelong friendships. I'm still in contact with students from the first time we ran the program in 1995, and I know David probably has contact, like you mentioned earlier, contact with students going back much longer than that. And I know they stay in touch with each other. It's routine for them to form a internet discussion group, a Yahoo group or whatever, and exchange messages with each other for a long, long time after the program ends. It's special to me to see how much impact and how much growth happens during these programs. Students leave saying, this is the best thing I've ever done in my life. And they follow up for years after, contacting me not just about, to reminisce about the program, but to ask mathematical questions, to talk about mathematics or whatever. And I think that's a true measure for success. Also wanting to come back and work for the program as a counselor in later years is another example of that sort of thing. Okay. I wanted to, before I conclude, I just wanted to comment on one other aspect of what I'm doing at Stanford. When T2 introduced me, he mentioned that I'm Deputy Director of the Education Program for Gifted Youth, which is the primary activity, it goes by the acronym EPGY, and our primary activity is computer-based distance learning. We have math courses going from grade school level through several years of university level, and these are courses that are intended for students who are ready to go beyond what their schools are offering. I think it's something that fits very well to the community that we're all trying to serve, completely unrepresented though, practically, at this program. So if anybody wants to learn more about EPGY and what it has to offer, I'd be happy to talk about that, privately after this session. So that concludes my talk. Thank you.
Questions?
Svez.
So maybe, did I miss, did you say how much it costs to run such a program? But I have a question. You didn't say, right? Okay, so that's my first question. And second, so the program has been running for 10 years. And every year you have to apply for a grant, or you apply for 3 grants, or whatever it is. And I have noticed that with programs that keep on going, it is harder to get renewal of the grants, because a lot of foundations, a lot of sponsors are interested in funding something new. And after 3 years, the interest drops down, even though your program may be successful. So how do you work around this?
Our main funding comes from a grant from the Howard Hughes Foundation that is part of a larger grant at Stanford funding similar programs, and the initial funding was for 4 years, and that has been renewed twice. So we're in our 3rd round of a 4-year grant. So that'll get us through 12 years, and that provides most of our financial aid for students. We also have additional grant funding coming from the math department, funding from the math department independently. We had the AMS Epsilon grant. Roby Vakil also has this as part of another grant. So we get other smaller amounts that kind of trickle in. And I think, that question could be addressed to the others as well. So I don't know if you want them to answer that.
We'll let this question to the end because we have 3 more presenters. And the next one, thank you very much, Rick. The next presenter is Mira Bernstein. She teaches at the Wellesley College and has been the director of the Canada-USA Math Camp since 2002. She had been involved with this math camp since 1997. That's when I first met Mira. First as a graduate student, instructor, and counselor. Then as the leading member of the camp's steering committee, and then the executive director and academic coordinator. She has also taught for several years at the Boston Math Circle when she was a grad student, and at the Berkeley Math Circle when she was a postdoc. Mira?
Hi, thanks. I'll try to be brief since we have lots of presenters waiting in the wings, and since a lot of what I wanted to say has actually been said by the previous speakers. But I'll tell you a little bit about Math Camp. It's called Canada-USA Math Camp, but Math Camp for short, although that I think a lot of the other people also use Math Camp for their programs. Math Camp is a 5-week program. We have 110 students, so we are significantly larger than the other programs that we've heard from, and that allows us to do some things differently. We are not affiliated with any college or university, which is both good and bad. It's good in that it allows us, and it's bad in that it sort of forces us to move from place to place during the summers, which is both more interesting and difficult. So last year we were in Maine. This year we will be in Reed College in Portland, Oregon. Eventually we'd like to settle on 3 places that we like and sort of rotate from year to year. So we have a 3-year rotation, but we haven't found 3 places that we like yet. So hopefully that's coming soon. Math Camp is unusual in that it's a program run essentially by graduate students, as well as people like me who used to be graduate students and ran it, and now I've gotten a little older but still pretend to be close to that age. So I'm an assistant professor now, but I'm of the people running the camp, I'm one of the oldest actually. So of course we benefit from the advice and the participation of more senior people, more senior faculty. We also have a lot of distinguished visitors, like a lot of these other programs who come to the program and speak. But the spirit of the program is very much one of youthful exuberance of a group of graduate students. And I should tell you a little bit about how the history of it, so you know how this happened. Math Camp was founded in 1993 by a Canadian mathematician named George Thomas, and it ran for a few years on a small scale, non-residential, in Vancouver. And its first year of large-scale operation was 1996. Now, George Thomas, or Dr. Thomas as everybody called him at the camp, he was a good teacher and quite a visionary in some ways to have founded this camp from scratch with no affiliation. But organization was not his strong point, and running a camp, he didn't really have a very good idea of how to do that. For example, it wasn't till after the camp in 1996 with 100 students ran that he realized that maybe a camp needed counselors. So in 1997, he brought in 4 graduate students. I was one of them. Dave Savitt, sitting over there, was another. He's the deputy director of the camp now. So he brought in 4 graduate students, and we were promised that we would hang out with the students and talk math with them and have time to do our research too. And we arrived in the first day, the day before the students arrived, to find that it wasn't even exactly known when the students were arriving the next day or how they would get there from the airport or exactly who the students were. And all of this was on disparate files on different computers, and we didn't have a printer. So this we found out, and no provisions had been made for basically anything. So for the next 5 weeks, we did very little math with the students. We ran the camp. And the math that was being done with the students we sort of didn't like it very much, because what was happening was that the students took an exam on the first day of camp, which then directed them into one of 3 programs, and they had no choice in the matter whatsoever. And what was going on in the 3 programs was not so bad. In one of the programs, they got a lot of visiting speakers talking to them. In another program, they had a course in computational algebraic geometry. In a third program, they had just a bunch of teachers teaching them different stuff. But the point is that all these students were basically forced to be in these programs, and they had no choice in the matter. And some of the ones, who were getting a whole lot of visiting speakers and not much else could have benefited from a fundamental course on, with a single teacher on the more basic topics, and vice versa. But they had no control over this. And so the 4 graduate students, together with one of the problem-solving instructors, Mark Krusemeyer from Carleton, who had just completed a stint of writing problems for the Putnam Committee, was on the Putnam Question Committee, basically proposed to take over the camp, and our proposal was accepted, because it had been clear at this point how indispensable we were to running the camp. So the next year, we brought in a whole bunch more graduate students and some undergrads to do the menial stuff that we'd been doing, some camp alumni, and more professors and more visiting speakers, so the present form of Math Camp was born, and it was born in this sort of burst of youthful exuberance and enthusiasm, and I hope it still retains that spirit. And the spirit is very much this: that math is there is so much of it, and there's so many different aspects of it, and people love it in different ways, do it in different ways, come to it in different ways, learn it in different ways. And basically, this is how professional mathematicians, there's a whole range of how they do it and what they do. And students should have that choice too. So what we do is we bring together a whole bunch of people. And the core of the staff is 8 or 9 graduate students. So and we get really, really good applications from all over the country, because these graduate students know that they are going to be the leaders of the program. So they are incredibly talented, dynamic, sort of creative individuals, and we try to get them from representing lots of different fields of math, but also visitors and some permanent faculty, problem-solving instructors, etc. So bring together this bunch of really amazing staff members, tell them, teach whatever you want, however you want, at whatever level you want, pretty much reasonable expectations for high school students. And then one poor soul has to put this all together into a schedule. So here's what the schedule looks like. And do we have copies to pass around? Well, I'll keep talking while. So, and then what we tell the students is, learn whatever you want, however you want. So at any given point, there are at least 4 things going on. We try to balance it so there are different levels. Courses, I don't know why this isn't coming up, but hopefully it'll come up. Courses range in, there we are. View full screen. View full screen, thank you. Here we are. Okay, so you might not be able to see all of this in detail, but hopefully you're also getting handouts. This is what the students get. So the first thing we tell them, of course, is don't go to every class in every slot. You're going to die. Also, you're not going to learn anything because you're not going to actually get to do any problems. So they are not supposed to go to a class in every slot. They choose where they go and when they go, and the rest of the time they spend thinking about what they've done and doing problems. So there's at least 4 things going on at every time slot, often more. The classes range in levels, so they're designated by sort of levels of mathematical sophistication required. So for example, if you look at the first time slot, there's a proof techniques course, so for sort of very basic, induction, pigeonhole principle, that kind of thing, and ranging to geometric group theory, taught by one of the visitors, which is mostly meant for alumni, so returning students who've been to the camp before and maybe already know some group theory. Here, if you look at this last time slot, there's Measuring Earth, which is an introductory course on sort of I guess it's a course on geometry as applied to map making and that kind of thing. There's problem solving, which I'll talk a little bit more later. This is contest type problem solving. Combinatorial game theory, combinatorial topology, and then a set theory course taught by the Moore method. So every year at camp there's at least one course being taught by the Moore method, which was talked a little bit about. Not the sort of super competitive style, but a class where students just get the definitions and theorems, but have to provide the proofs on their own and then present them to each other. And then Cookies and Math is a communal office hour where all the instructors are sort of in the same place and students come and talk to them about it. But of course, the instructors, being most of them graduate students, they all live in the dorms with the students. They interact with the students in many different ways aside from just the formal teaching, as a lot of people have pointed out. It's very much, and the summer program is very much a mathematical community. And especially with the instructors being so young and close to the students in age, they really get to become sort of friends with them. And so, you know, this is not, Cookies and Math is not the only time when you ask your instructors questions. You also ask them at 1 a.m. Let's see. So as a result, what happens is each student has an advisor. Of course, we wouldn't expect them to navigate this all on their own, who consults with them on what they might want to be doing. And each student really gets to take control of their own education and decide what they want to get out of the camp. And there are many, many different things you can get out of the camp. You can go to a lot of courses and get a certain breadth of vision and a big picture, which really, having talked to our alumni, it really helps them later on when they go into their undergraduate courses, even if they don't remember the exact details. They sort of have a sense of how this all fits into the big framework of mathematics. You can concentrate on one course and learn a subject really well. You can, at Math Camp, and I think we're actually sort of different from all the other summer programs here except for MOSP, you can do contest-style problems. We have problem-solving classes here and here. But those are only 2 classes, so you can't only do that. So in other words, kids who come and say, well, we want to do contest-style stuff, we say, sure, go ahead and we'll teach you contest-style stuff. But, you know, look at all this other stuff out there. Look how interesting that is. Come try that. And so we often have students who the first year they come to Math Camp just are like contest, contest, contest. And the second year they come to Math Camp, they don't even go to the contest stuff because they realize what else is out there. A lot of students, we also try to bring in people who are not mathematicians to talk about how math is applied in their field, and we try to bring in applied math courses, so some students are interested in that. So basically, students get out of it what they want. It's a real sort of, the schedule, I don't know, whenever I look at it, it's always inspires me with this feeling of sort of infinite potential, like look at all the stuff that's out there and look at sort of how much you can do with it. And the courses vary in format, so some are more sort of interactive. They're all interactive, but some are more lecture style, some are more discovery style. And as one student put it, basically gives you the feeling that math is anything you want it to be. So that's probably it about Math Camp specifically. I wanted to say a couple of words about summer programs in general, although most of what I wanted to say has actually been said much better than I could ever say it. But one thing that has come up in the past few days is that the network of math circles is localized to a few places, you know, San Francisco, Boston, New York, maybe a few other places, but there's vast stretches of the country uncovered by this network. And of course, one thing we want to do is to create math circles in all of those places, but it's not necessarily possible. Well, the summer programs, you know, we can't go to those kids, we bring them to us. And it's also a way that people have been talking about sort of how do you get through to all the teachers in the schools. Well, you know, these kids, if you get a kid from, you know, one of these schools which is not connected up to the network of contests or whatever, then they make sure the next year that their school gets the Mandelbrot competition and their school gets the AMC competition, even if it didn't have before. And so in the interest of this, actually, Math Camp, throughout its history and throughout its quite sort of difficult financial position for much of its history, has done one thing always, which is send a brochure to every high school in the US and Canada, despite the fact that this costs us a great deal of money. And we know this isn't enough. We know that grassroots sort of work on getting teachers interested is necessary. We can't go to every school in the US and Canada. And we recognize that probably 50% of these brochures get thrown right into the wastebasket. On the other hand, we do get students every year who come from these schools which are completely unplugged in. So like Rick was saying, from remote corners of California, well, we get them from remote corners of everywhere. Not that many, unfortunately. Most of our students still come because we also send brochures to contest high scorers on the AMC, and most of our students come from there. But there are a few every year who come from these middle of nowhere places, and it's really amazing the way their eyes light up. I mean, it's really amazing what a revelation this is to them. And then they go back to these middle of nowhere places, and there's one more school that's plugged into the network, so that's a great thing. And the other thing I wanted to emphasize is that I think all of the summer programs have financial aid, have funding for students, for disadvantaged students, including full scholarships. So, to all the math circle people out there, send us students, send us all students. And I think there's a misconception a lot of times that, well, math circles are free, but camps cost money. Well, camps do cost money. They cost a lot of money to run. But all the camps give financial aid. So it's not really a matter of money. I think that's all I wanted to say.
Questions? Yes.
Do the courses you've listed up there continue throughout the 6-week program? For example, Fernando Gouvea's Mysterious Numbers of Professor Hensel?
So here, Fernando Gouvea is one of the visiting speakers. So his course, he was only there for 2 weeks. So his course only went on for 2 weeks. Many of the courses continue, for example, a lot of these are long-term courses. So they continued for the whole 4 weeks. Actually, so the program lasts 5 weeks, but what we've found works best is that if we give them the schedule for 4 weeks, and then in this whole spirit of math is what you make of it, in the beginning of the 4th week, all the instructors write up all the things they didn't get to teach and they really wanted to teach. So it's a 9-page long description of courses, and we give this to the students and we say, vote. What do you want us to teach? What do you want to hear about in the last week? And so they vote, and that ensures that they actually come to the courses, because we found before that in the 5th week they get a little tired, so they kind of, but if they voted, then they really come and they do it. So some courses, for example, here you see there's one-off sort of, this is one-time lecture, this is a one-time lecture. It's the same person teaching in all these time slots, so she can tie them together if she wants to, but so sometimes it's just, a student says, oh, I'm done with my hard courses for the day, but I want to go and hear something cool. So they'll go to a one-time lecture, but other things last longer. Some things last for 2 weeks and then are replaced by other things. Planning the schedule is a great ordeal, and nobody's ever entirely happy with it. But
do you have things like homework or and regrading? That could you describe that?
No grades. Oh. Yes, so there are problem sets that go with the classes. It's up to the professor how much they want to, whether they just want to discuss the problems in class or actually grade the problem sets. But there's definitely, another thing I forgot to mention is that there are students do independent projects, or at least they have the option to. They're not required to do anything, basically, ever. So they're not required to go to any given class. Of course, if they don't go to any classes, we complain to them. But that very rarely happens because they're there because they want to be.
But do you have a problem with students being really on in class, but then they don't do as much stuff, don't have as much to written up afterwards?
That can sometimes be a problem. And we try to encourage them to sort of do more writing. I mean, the classes are interactive, so they learn that way too, and they do work on problems, but it's true that sometimes it can be a problem that they get excited about all these classes, and so they don't do enough on their own, and we do what we can to discourage that, but it is a possible danger. There are independent projects also that they work on, which are done in the same way, so all the staff think of topics that they're willing to offer projects on, and the kids get to choose, and in the end they have a project fair. And those students that do projects, which is a large portion of the camp, they certainly have practice on writing things up and presenting things quite a bit, and the projects are also really great.
Thank you very much. The next presenter is Zuming Feng from the Phillips Exeter Academy, my longtime friend and collaborator. He has been involved with the Math Olympiad training since 1996 as an instructor, and now is the director of the academic director of MOSP. He serves on the USA Math Olympiad subcommittee and is the leader of the US delegation in the International Math Olympiad. He will talk about the summer program, the Mathematical Olympiad summer program, that is. Zuming?
I want to thank the organizer of this, so we really get a chance to meet everybody. And you know, I know many people. I have read many people's book and used many materials, and now I can thank them in person. I'm going to talk about MOP. I think the difference of a MOP as a math camp compared to other math camps, because other presenters really said many things about the advantage of math camp, and they really described the mission statement of math camp much better than I do. So talking about MOP, I'm distributing this because this is the most enjoying part and the challenging part of MOP, is making up problems to test our best students, and also the most difficult part. So that's why I want to explain this at the end. So I would like to ask for helps from all the mathematicians around and your networks. MOP is different from other camps in the sense that it's free to all the students, so that's a big draw, and also so that makes us worry very little about our recruitment. And usually after the USMO, we start to call people, and all the experienced students know at that afternoon they are waiting for that phone call. So that's the easy part of our job. And it's also a camp has been there for what, about 30 years, and it's run by different academic directors or the MOP leaders, and along the way people already set up a very modify it year by year, and now for me I just take over lots of what they established and don't have to do too much. So. Comparing to other camps, MOPs have a more practical goal. There is immediate results people want to see. Doing well on the IMO is not a definite requirement, but we cannot have 3 years in a run as good as Team Canada. Sorry, Roby, nothing against that. Or doing as well as Stanford did on Putnam, for 5 or 10 years. Just sorry, just kidding. The goal is there. It's not, because I still believe U.S. education, besides all those loopholes, we still produce the most creative students. So as a team, we should do well. So that's our own requirement. So that's the difference between MOP and other camps, is we want to see that results, consistently. And also the MOP is in University of Nebraska. They fired their football coach even though after he won 10-3. So we have to be a little bit careful, on the right. So MOP have about 30 students on average, but right now we get enough support for about 60 students, very likely. And last year we had 60 students. So how these students got selected? They are coming from different components. The top 12 students are automatically invited. The top 12 USMO winners are automatically invited because they were competing for the position for representing the USIMO team, the top 6. And then the next 18, next 18 is all the high scores from the underclassmen. So that's 11th grader or younger. So that's composed of regular 30 students. And then the next 30 students, we expanded them up last year. The 30 students is for the future, developing our own future. So we invited the 30 ninth graders who are able to participate in the USMO. And then also some very good students in 10th grader. So that's where those 30 students come from. So they are the future of the team. So instead of telling them, they are the top group or whatever group, we try to candy code them a little bit. So we tell them they are in the black group, blue group, or red group. But if you are doing karate, that's clearly the rank of karate belts. And that's idea from Tito. And for a regular mob day, we work, the length of mob is between 3 to 4 weeks. And we usually work 6 days and have a 1 day off. So it's quite intense. And for a particular day, right now we adapt the format Kelly was talking about is in the morning we have a lecture, and in the afternoon we have a problem session, and then we have free time, and then in the evening we have a lecture. Because I think by the same reason we feel like it's much better give them free time in the afternoon because Lincoln is very hot. They don't have too much to do. And during the night, we can put them more focused to work together. And during that free time, we encourage lots of, their self, structured games, sports or whatever, because I think playing sports is very important because the students understand. That's one thing I like, the analogy, some part about sports camps is, when you play a sports, you feel like if you make a bad play, you can easily accept it. And that helps students to deal setbacks because mob, the test is pretty hard and they have to learn how to deal with the setback. So in the morning they have lectures, and then we have lots of tests during the afternoon. And it's about, every mob is about 12 tests, right, Tito? And the making up those problems is the most challenging part because on one side, I would love to have Reed or Gabriel students like that every year. They come in as a 7th grader, they improve, and then they be on the team forever. But on the other hand, it makes our testing so difficult because you can't give them anything they have seen before. So that means 7 years of totally different test problems. Right? And I think that's a very natural, good thing because they push us to push them. So we have to look around and find the best materials we can find to really make them have, try to, well, I quote Roby says is, or somebody said yesterday is, they will like the problem after the test, humming the problem after the test, because for me the most intriguing thing is the difference between that real math and the math contest. And we cannot do too much on the research, but I hope the problems are intriguing enough to let them be able to do those math research later on. So the tests, the mock lectures have various formats. There will be teachers who, certain teachers will do different. One teacher will do different things, depends on, their the topics. Sometimes they run the lectures. Sometimes they will get more students involved. go to the board to present their solutions, to talk about it. And sometimes we just run one problem and talk about the 10 solutions about this problem, so students gain confidence about where do they start. They are always able to finish it if they think more carefully. So those kind of things. And another thing is I always want the team to be intelligent, but on the other hand, they should get away from that eliteness. I want everybody to feel like they can contribute. And so lots of, group work are encouraged. So the older students teach the younger students, and then suddenly they realize some younger students, maybe they are inferior on certain test scores, but hey, on another problem they have not seen before, the younger students have better ideas, so they learn from each other. So we have lots of contests like team contest. The team contest is basically we used lots of Olympiads around the world the previous years and make the students work on them as teams and challenge each other. And Melanie might not like the competitiveness about that, but that's one thing to let students, to work together, because now they have to, really help each other to understand how to solve a problem. And then another thing they develop is on the back of this packet. I'm not very organized, the back of the packet actually is the one I want to talk first. It's called Elmo. They have tons of ways to explain what is Elmo. I think actually Melanie started it. So Melanie and Paul started in 97, 98, so that's another thing I want to, to make this mob run is because of all those students coming back as the graders and later on instructors, and they bring in wonderful ideas. And so Melanie doesn't want to be in competitive on the team contest, so she make a contest to let other people be in competitive, right? So this test is the older students sit together, design a contest for younger students. And that's a wonderful thing. They have to organize the contest, split them into different teams, and each team have a leader, and they have to sit together to propose their problems. And then after the test, they have to grade, and they have to do pure IMO style. It's coordination. So the leader works in with the paper, proposing the points, and then the coordinator will give them the points and the discussion. So this, improve the students' desire of writing problems and writing good problems. And then another thing is this gives students the opportunity to be very friendly, criticizing each other's not really criticizing, being critical with other teammates' work. And they understand after being the leader, they can tell their team members, man, you give me all those junks, how can I give you points? Get points for you. So now in that way, we enforce the students. Now you understand how important is writing your solution clearly means. Because I'm pretty sure Kiran, T2 have that experience when we in the IMO, when we get a paper, we say, man, how can we get points from this kind of writings, right? So in that way, students learn from each other, because they were put in that role. They understand we better improve our presentation. How do we really express ourselves better, right? So those are the things we do in the mob, and then because we have to write so many tests to challenge our best students. So this is something I want to say is I want to give people an idea how do we get all those problems from. So for example, on the mob, for the lower level students, we ask questions like 1, A and B. They are very routine, I cannot say routine, but very regular, algebra problems about polynomials. And then we also have to, for example, part 2, I group those 4 problems together because they are more or less come from Math Monthly. That's the problem I've seen, and I think Zvezda gave me one of them last year from Monthly. there are variations of types of problems you have seen before, but it's new. It's the first two problems are certainly related to the Euler function, and then Tower of Hanoi, everybody knows, but they just change it a little bit, but at least it's new to the students. And then part D is about in sets, chain of, containing sets. And people used it in other math Olympiads, and this problem also appears in the Math Monthly recently. So that's how that's our problem source, different ways of getting them. And the problem 3, for example, is again for, it's basically another way of asking what Mark did the first day about that cube. How do we know 0, 1, 2, 3, 4, 5, 7 is basically a binary, representation of all those cube coordinates, and then we find another way to ask them. So, and what else? And the 4, it's also a skill we ask students a lot. Is about, when you talk about primes, largest prime, the smallest prime, and how to use them well, and those kind of things. And problem 5. A, B, C, all of them are coming from, my own classroom discussions. For example, part B is when I teach in my high school, the students ask me, how do you know vectors 6, 2, 3, you can move them around, you can get another vector perpendicular to it. And they still have the integer, parts or whatever. So, I changed this a little bit more to give it to the mob, but a little bit harder. And then problem C is another example. This one is coming from Arnold contest a year before, and this is coming from Amy, but we asked them a little bit more differently and become a Math Olympiad problem. So, and then, the next problem, this chunk of problem, I put them together not because mathematically they are related, but because all of them are proposed by our previous students, and they were putting certain tests. I think the first 2 was by Gabriel, and then this one was by. This one is by Gabriel. This one is by Reed, and this one is by. I'm not sure who did that. Well, anyway, they are all presented by our students, and then there are many problems, from the different kinds of math magazines, and then we developed, from new brain teasers like problem 7, 8, and I won't keep this short. Finally, I want to say is what's the difference between this math contest right now and the math research right now. If you start from problem 14 to the end, they are more or less all those problems are come from IMO shortlist. I put them there only want us to see that all these problems are somewhat so close to math research right now. And I think this becomes a trend of really how those highest level of contest is run because again, good problems coming from research, and for the people who run in the mob, this is the most help we need is come from the research math community to give us good problems to support our bloodline of getting more students interested in math, and they see what is the front line of math can go. And that completes my introduction. Yeah. One more thing. I think Steve Dunbar, who is in charge of AMC American Math Competition, will send everyone right at present email, so you don't think this is really a spam email. Discard it. He was looking for all the people's help on all levels of AMC competition. If you have your network, can give us good problems involving your nice new ideas or researches, that would be great.
Thank you, Zuming. I'd like to speak to this just very, very briefly. We need very good problems because there are so many exams that we need to put together. And it's to the easy side to the most difficult ones that you can devise. And making problem for USIMO is very challenging. We only had a few submissions this year, and obviously we will be able to put together an exam, but having more and more problems would be beneficial. Also, to submit questions for the IMO. As Zuming said, many come from research. We were able to have problems on the short list, but it's more and more competitive, and we need good problems to bring to the IMO committee in order to put together an exam. The next and last presenter from our panel is Abby Thompson. She teaches at UC Davis, where she was since 1988. And she's the director of the Cosmos math program at UC Davis. She will talk about this program and more.
I'd also like to thank the organizers, and I'm now in the unenviable position of keeping you all from your lunch, so I really will try to be brief. I wanted to first respond to a comment I think Tom Roby made about how we count papers in math. This isn't really relevant to my talk, but in fact, we believe at the University of California that all deans go to school before they are allowed to assume their position as dean, and they learn how to count collaborative papers. And in fact, I think with the co-authors that you had described on your papers, you would in fact have 1 1/3 papers counted to your credit. So there's something in the culture of research mathematicians that one of the many things I think that needs to be worked on. Let me describe the Cosmos program. It's the newest program, which is why I'm last here. Cosmos is a 4-week residential program in math and the sciences. It's the California State Summer School for Math and Science, and if you can make that turn into Cosmos, you're better at it than I am. But they decided that would be a cool name. There are 4 campuses at the University of California that support Cosmos programs. 3 of them have been running for 4 or 5 years. 1 of them is new at San Diego. Each site is designed to have 150 students. The selection criterion is academic excellence. And one point I want to make is that that's an extremely unpopular selection criterion from the point of view of the University of California. This is something that's been imposed on it. By some miracle, the funding for this program got through the state legislature with that as the clear and only criterion for admission to the program. So we look at essays, grades, test scores, and teacher recommendations for admission. This program is different from the ones that have been described so far in that it's in math and the sciences. So we don't have 150 students studying math. The students are in groups of roughly 20, although it's been pointed out to me that that makes it tricky to come up with 150. So roughly is key there. And each group is in a particular area. So at Davis we have, among others, a geology group, an engineering group, and a math group. Mostly, I have to say, because I'm a mathematician, and so that's what keeps that as part of the program. A lot of the regular research faculty from the campus teach in the program. The secret to involving them is not very mysterious. We pay them a lot. I don't think it would be possible otherwise. The challenge with involving regular research faculty is to get them to do something other than to lecture for 20 hours a week. That does not work very well with a small group of very intense high school students. I'm not sure it works very well in any case, but it's much more obvious over the course of a 4-week program. The topics are determined by the faculty. I look for faculty who are willing to teach in the program and say, what would you like to do? And I try to describe the population of students that they're going to be dealing with. The program is a bargain for California residents for whom it's mostly designed. This summer it's $1,600 for the 4 weeks. And we have about a third of the students on full or partial scholarship, mostly full scholarship. That's based completely on financial need. Every one of our groups has a high school teacher associated with it. The high school teacher goes to all the classes, and the high school teacher is also responsible for running a writings communication course concurrently with the clusters. Each group is called a cluster. That was a big improvement over our original idea, which was to have English graduate students running some kind of writing course. The failure there was astonishing. There just didn't seem to be any way to convince the English graduate students that we were interested in anything other than verb-subject agreement and stuff like that. So having the high school teachers who are all math or science teachers and have some kind of reasonable background for the cluster that they're working with, having them be in charge of this course, and the course has a goal. Each student in our program is supposed to produce a project over the course of the month. And so there's a very specific thing that they are supposed to be doing within this writing and communications course. That seems to be working. Another thing is that the high school teachers who are affiliated with the program are also fairly well paid, which is, I think, a big draw for them. So the program has been running for 5 years. Last year at our campus we had about 400 applications for 150 spots. So we are at this point, I would say, getting the students that we would like to be getting for the program. The goal of the program, this is partly in response to the question of elitism. The goal of the program is pretty much to salvage the few. There is a feeling that the general education system, particularly in California maybe, is not producing enough mathematicians and scientists. Trying to fix that whole problem is certainly too much for me. And I haven't heard of any really coherent plan to do it. And in the meantime, our PhDs in math and the sciences have to come from somewhere. And so we are trying to reach the students that have the potential to go on for PhDs in the sciences. Our success, which is going to be difficult to measure, will be how many students from our program that go on to get PhDs in the sciences that would not have otherwise. And that's tricky because it's clear that a lot of the students that are in the Cosmos program are going to go on that route regardless. So we have to make a special effort to try to reach the students that would not have otherwise and bring them into the program. The demographics of our program, the male-female balance is pretty good. In fact, it tends to be slightly more girls than boys overall. It varies by cluster quite a lot. The girls are overwhelmingly more interested in the biology clusters. Very few are interested in engineering. For some reason in math we're about even, so I'm pleased about that. I'm personally baffled by the early age at which somehow this idea that girls are interested in biology. The interest in biology is very straightforward. It's they want to take care of someone or something. They want to be pediatricians, they want to be vets. As I read through these applications, I said this yesterday to someone, if I just can find a girl that wants to improve on the nuclear bomb, she's in. That sounds terrible, and but let's not do that. But how to get girls interested in math, but also in engineering, is something of concern to me. The underrepresented minority representation in our program is roughly the same as in the UC system as a whole, which is not great, but we certainly, there are large numbers of underrepresented minorities in California, and so we are reaching some of them, although we would like to reach more. One benefit of a residential program that has been mentioned in passing, but I would like to emphasize, is that it does give us an opportunity to bypass the question of parental support. If we're able to reach to certain students, and we can then bring them to campus where they have this wonderful peer group, we can sometimes reach students who don't have this continuous, steady support from their parents to pursue their interests. And I would say that I would guess one feature common to almost all of the Olympiad winners and many of the participants in the math circles is that their parents are not necessarily pushing them, but encouraging them and supporting them. And that's a very limited group of students. And I think that this explains a lot of the demographics of the students that we're reaching. And it probably explains the third generation American question demographic as well. And so any way that we can, that also sounds terrible, but bypass the question of parental support, I think we should possibly work on. Another aspect of the residential component that has been mentioned many times is this instant sense of community that the kids have. It's the one thing that I say to parents when they first come. We have a big meeting and all the parents are there, and as far as I can tell, 10 family members are there with every child. And I make this comment that students in high school feel that are good in math and science can feel very isolated, and this program will make them feel less isolated, and they'll have people to talk to, and that's the thing that parents hear, and they'll come up to me afterwards, many of them, and say, that's what we've been missing, that's what we'd like. A drawback of the residential program is this intense sense of community that the students get, because they're so enchanted with the fact that they're surrounded by all these kids that have the same interests that it actually can be distracting. It's great. But it's, sometimes I worry that we could actually have them all standing on their heads in a corner for 6 hours a day, as long as we let them live together in the dorms, and they would be perfectly happy. And that may be true. But we try to get them to do, interesting academics while they're there. Another drawback of a residential program, which I was unaware of and am learning sadly, is that if you have 150 high school students together for a month, there will be certain problems. Some of them, I kind of like the idea of free time in the afternoon and activities in the evening. That hadn't occurred to me. That's one of the problems. But just, I mean more specifically, there will be some unstable students. There will be some I have to deal with things that I never dreamed of having to deal with. And I'm sure high school principals, know about these things all the time and deal with them all the time. But it's not something that I, as a mathematician, was ever trained to work with. I just want to make a couple of comments. That's pretty much all I have to say about the Cosmos program, but I have the microphone, so I just have one more minute because I have a couple of comments on speakers from yesterday and previously. The first one, and I've touched on this already, is I think that we have to make more of an effort to convince the community of research mathematicians that this is important. Actually, embarrassingly to me, the subject that I have the most difficulty in recruiting regular faculty to work is math. And fortunately, I'm the fallback faculty person, so I can always teach, and I do teach in the program. But in the other fields, it's easier, and somehow it's more standard. So it's other lab sciences are better set up for regular faculty to do this kind of activity than math is. And you know, it's basically seen as a foolish thing to do if you're a research mathematician. Spending your time this way is not good for your career. So I don't know why the tradition in this country developed so differently from the way it clearly did in, for example, Russia, where it seems like it was a very respectable thing to do, but here it's not, and we're not addressing it well. And then a couple of phrases that have been used several times that make me personally very anxious are, here's one, exceptional mathematical talent, and another one is profoundly gifted. So this makes me very nervous, because I'm a mathematician, and I would never have said either of those things about myself as a kid, and I don't think there would have been any indication. I was good at math and I loved it, but that was pretty much it. So I would say, unless we're only looking for the young Bill Thurston, which I don't know how you find that, these are exaggerations. And what we should be looking for are kids that are very good at math. I mean, you know, they have to have some talent and are really, really very interested in it and love it and are willing to spend time on it. That's it.
Yes.
Since it's not yet noon, so we have a few more minutes, I thought I'd ask a question. I'd like to know from, I guess, primarily the non-MOP panelists, A, what it costs per week to run your program, and B, what you look for in a student when you are selecting your, I mean, obviously it's a sort of a minimal mathematical interest and talent, a baseline sort of, but beyond that, what do you look for in your students when you're admitting, when you're selecting?
I'm trying to do the computations in my head of what it costs per week. I think it costs about, no, a lot more than that. Gosh, per week. Yeah, 600, actually, you're right. Well, that's right. So, but it's very complicated. The full camp fee is $3,200, but more than half the camp gets a tuition reduction, and lots of people get scholarships beyond that, and you know, and plus we have outside funding, but probably about $600 per week, per student per week. Operational. That's right.
So if you had no financial aid.
So.
There is no profit.
No, but I think that's about how much it costs.
Oh, I see.
That is actually how much it costs. Yeah.
I think we charge students $1,889 for the full 6 weeks. That's full room and board, tuition, and such. That money, of course, less than that, we get some money, of course, from financial aid. Essentially, costing the program costs about twice that. So we get about as much from outside sources as we get from students.
So that's also like 600.
Yeah, it comes out to about 600. And I forgot to mention, I have handouts here too that you're welcome to have. And I also forgot to mention, I have the microphone now. I also forgot to invite people to come visit the program. Please do.
I don't actually have a very good sense for the numbers. I haven't thought about them in a long time, so I think it's probably on a par with this. As I recall, running a 6-week program at Promise was somewhere around $200,000, $250,000 maybe. And I think that might have been in a year when it was NSF funded, so maybe that's a little bit higher than what, you know, the minimum they could get away with if they were really working hard. But if that doesn't divide out properly, then just think I'm crazy.
Everything costs more at Stanford, so it's about $800 a week. So for the 4-week program last year was $3,100. That is about pretty close to cost. About half of the students get some amount of financial aid, and maybe a fifth of them get full financial aid. You also asked about admission criteria, but since the others didn't answer that question, maybe we'll do another round.
I think the Cosmos program is not very representative because we cost a lot more. So the cost for the 4-week program is actually around $5,500 per student. But you have to realize that I'm dealing with biologists who want, incredible equipment and lab stuff for their students. So for the math part, my guess is it's about the same.
Well, I'm the mob person, but I like to say a little bit anyway. We have to worry about our cost too. It's not like we have infinitely many funding, That's why we're in Lincoln, Nebraska, our camp.
For admission criteria, we look primarily at grades in math and science, and also to see whether the students are taking advanced courses in math and science. And I would say that combined with their teacher recommendations are the two most important things that we're looking at. We do also look at California. All California students take tests, standardized tests every year. So we do also look at those test scores, but they were never really intended to be used that way, and so they're more a question of whether we've missed somebody.
In your age group, Abigail?
Students entering grades 9 through first year of college. Actually, we have some graduating seniors.
Yeah, SUMAC targets students entering grades 11 and 12. We look at test scores, grades in school, teacher recommendations. We have our own admissions exam, so a set of very challenging math problems. And we also ask them a bunch of questions about why they want to come. So we look for people that express their heart is in the right place. If they say, I want to spend the summer on Stanford campus and I want to be away from my parents, they're probably not going to get in. We also try to get a geographically and culturally diverse population. So we do look at the group overall as well as the individuals.
You're looking for the women who want to improve the atom bomb too.
No, not that kind of diversity.
I see. So I think Promise and the Ohio State program used to take students pretty much after their junior year. And then Ross started working with younger people, and so I think Promise and Ross are both, maybe Ross is even a little younger than Promise these days, but so Promise is typically after looking for people who are becoming juniors or seniors, maybe occasionally a little younger than that, and Ross is probably half a year on average younger, I think. And the criteria are, again, some sort of an interesting test, writing up solutions to problems, and there's enough open-endedness into them, and you can tell by the way they write it up whether they, come from a contest-solving background so that they only write down like the minimum key points to make it clear to the grader that they understand what's going on but leave out anything else, or whether they haven't had that kind of experience at all, and then they tend to write things that maybe aren't nearly as coherent but may show that they've really explored things in a different way.
We asked for a sponsor recommendation. We asked the student to write a friendly and informative letter indicating why she thinks this would be a good way to spend the summer. And then we have what we call the interesting test. The interesting test, the ideal question on the interesting test is one which introduces an idea which is quite new to students, gives them a little bit of sort of fill-in-the-blank type stuff just to make sure they understand the vocabulary and have some sense of success so they can answer a couple of questions, and then has some deeper questions asking them